Every galaxy is being steered by an invisible current. For centuries, we saw them as lonely islands adrift in a dark sea, but this was a profound illusion. The truth is far more magnificent and interconnected. Galaxies are not isolated at all. They are passengers on a vast, hidden river system, a flowing architecture of dark matter and intergalactic gas that dictates every move they make. This structure is known as the Cosmic Web, and it is the ultimate puppet master of everything in the cosmos. By the end of this exploration, you will understand the invisible blueprint that controls the destiny of every star city, including our own Milky Way. We will trace how a whisper from the birth of the universe grew into this colossal network, and discover why a galaxy's past and future are written not in its stars, but in its position on this universal map. What does it feel like to know your entire galaxy is riding a tide you cannot see? That early view of the cosmos was a trick of perspective. When astronomers first trained their telescopes beyond our own galaxy, they saw a scattering of faint, fuzzy smudges against the blackness. It looked like someone had tossed a handful of glitter onto velvet, a beautiful but seemingly chaotic splash. Each galaxy appeared as a lonely, self-contained island of light, drifting through an endless, empty void with no discernible pattern or purpose. This was the universe we thought we lived in for most of modern astronomy, a quiet, sparse, and fundamentally random place. It was a comforting simplicity in a way, but it was also a profound illusion. Our instruments were simply not powerful enough, and our maps not wide enough to see the truth. The breakthrough came not from looking deeper at a single point of darkness, but from stepping back to see the bigger picture. Ambitious new surveys began to chart the positions of millions of galaxies across vast swaths of the sky. They did not just look out, they looked around, creating a three-dimensional atlas of the cosmos on a scale never before attempted. And when those billions of data points were plotted, the illusion of randomness shattered. The galaxies were not scattered like confetti, they were arranged. They formed immense, delicate chains and sprawling, flat walls. They gathered into dense, spherical knots where thousands of galaxies swarmed together. And between these brilliant structures lay enormous, terrifyingly empty voids, bubbles of near-nothingness stretching for hundreds of millions of light-years. This was the first glimpse of the cosmic web, a pattern of staggering grandeur and complexity. What looked like chaos was, in fact, a masterpiece of architecture. The glitter was not randomly tossed, it was carefully embroidered along the threads of an invisible tapestry, so the immediate question becomes undeniable. What kind of force could possibly arrange the universe on such an impossible scale? The answer lies in a whisper from the very beginning of everything. That tapestry is the cosmic web, the fundamental architecture of our universe. To understand it, think of the universe not as a simple, empty box filled with galaxies, but as a single, interconnected structure. The cosmic web is the name for this immense framework, the largest pattern we can observe in all of existence. It is the scaffolding upon which every visible thing is hung. This framework is built from a few distinct, awe-inspiring features. First, there are the dense knots where gravity has won a tremendous victory. These are galaxy clusters, bustling metropolises containing hundreds or even thousands of galaxies all bound together in a swirling, gravitationally tangled dance. Then, stretching out from these dense hubs are the filaments. These are the grand highways of the cosmos, long, slender threads of dark matter and gas that connect one cluster to another, forming a sprawling, three-dimensional network. Where several filaments intersect or run parallel, they can create vast, flat sheets called walls, which are like great continental plates of galaxies. And finally, surrounding all of this brilliant structure are the voids. These are the deserts of space, unimaginably vast regions that are almost completely empty of galaxies, dark and quiet bubbles that make up most of the volume of the universe. So the cosmic web is not one single thing. It is this entire ecosystem, this delicate balance of crowded cities, luminous bridges, and empty expanses. Every galaxy we see, from the mightiest spiral to the faintest dwarf, exists somewhere on this universal map. It is either part of a dense cluster, strung along a glowing filament, embedded in a great wall, or sitting alone on the quiet shore of a void. This is not a metaphor. It is the literal, physical structure of reality on the grandest scale. Our place in this web, therefore, is not just a location. It is a destiny written by the shape of the space around us. But who built this map and what holds it together? The blueprint for the cosmic web is written in gravity, but not the gravity of the stars and galaxies we see. That visible matter is merely following a script. The true author, the architect that carved out the filaments, walls, and voids, is something we cannot see at all: dark matter. This mysterious substance, which does not emit, absorb, or reflect any light, makes up the overwhelming gravitational skeleton of the universe. Think of it this way. If the cosmic web were a magnificent, glowing neon cityscape at night, the dark matter would be the steel girders, the concrete foundations, and the hidden wiring holding everything up and in place. We only see the neon lights, the galaxies, but they are tracing the shape of the invisible framework beneath. In the earliest moments after the Big Bang, the universe was a nearly smooth soup of particles, both ordinary and dark. But it was not perfectly smooth. There were tiny, random ripples in density, whispers of more and less, and dark matter, responding only to gravity, began to clump around those whispers. Because there is so much more dark matter than ordinary matter, its gravity dominated the construction project. Over billions of years, it pulled itself into an immense, tangled network of strands and nodes, the gravitational valleys and mountains of the cosmos. This is the dark matter skeleton, then the ordinary matter. The gas that would become stars and galaxies simply flowed into the grooves carved out by this dominant gravity. Like water finding the path of least resistance down a mountainside, the luminous stuff of the universe followed the gravitational contours laid down by the dark. It pooled in the deepest gravitational wells to form galaxy clusters. It streamed along the dark matter filaments, lighting them up with galaxies like beads on a string. It left the voids largely empty because there was no gravitational pull there to hold onto it. So when we look at a map of the cosmic web, we are seeing a dual reality. We see the glowing aftermath, the ordinary matter that lit up the blueprint, but the shape, the flow, the very destiny of every galaxy is dictated by the invisible hand of the dark matter scaffold. This means a galaxy does not choose its path. It is riding a river of gravity that was set in motion when the universe was an infant. This leaves us with a fascinating detective story. We know the dark matter scaffold exists, but how do you map something you cannot see? Astronomers face this challenge by tracking the one thing that does respond to the scaffold's irresistible pull: the galaxies themselves. Think of it like trying to chart the shape of a valley on a foggy night. You cannot see the ground, but if you watch where all the water is flowing, you can trace the slopes and the riverbeds with perfect clarity. Galaxies are that water, and their motion reveals the landscape. The primary tool for this cosmic cartography is something called a redshift survey. Here is how it works. When a galaxy moves away from us, the light it emits gets stretched, shifting toward the red end of the spectrum, like the fading horn of a train moving into the distance. By measuring this redshift very precisely, astronomers can calculate not just how fast a galaxy is moving, but because the universe itself is expanding, how far away it is. This gives them a third dimension. A project like the Sloan Digital Sky Survey did not just take a pretty picture of the sky, it meticulously measured the redshift of millions of galaxies. Each measurement became a single dot in a three-dimensional map, with its position defined by its direction in the sky and its distance from Earth. When you plot millions of those dots, the pattern that emerges is not random noise. It is the luminous trace of the cosmic web. You see galaxies lining up along invisible threads. You see them crowding into dense clusters at the intersections, and you see the stark, empty gaps of the voids. The map is made of light, but the shape it reveals is the fingerprint of dark matter's gravity. Every galaxy in that survey is a witness, testifying to the pull of the unseen structure it is riding. So when you look at one of those breathtaking visualizations of the cosmic web, with its delicate filaments and cavernous voids, you are not looking at a guess or a simulation. You are looking at a census, a direct plot of where the universe put its cities and towns, and that map tells us exactly where the gravitational valleys are deepest and where the rivers of dark matter are flowing. Our own Milky Way is on that map too, which raises a compelling question. Where exactly are we in this universal metropolis, and what does our address tell us about our past and our future? Our cosmic address places us on the outskirts of a sprawling galactic supercluster, but to truly understand the forces moving us, we must also understand the immense, silent spaces we are moving away from. If the filaments and clusters are the brilliant cities and highways of the universe, then the voids are the great, empty deserts that define their borders. These are not small pockets of nothing. A cosmic void is an almost incomprehensible expanse of near emptiness, a spherical region of space that can stretch for 300 million light-years or more, containing only a handful of isolated galaxies where there should be thousands. They are the dominant feature of the cosmic web by volume, making up most of the space in the universe, and their emptiness is not passive. It is a powerful, shaping force. The motion of every galaxy is defined by a push and a pull, a gravitational landscape where you are drawn toward the dense mass of filaments and clusters, and equally, you are repelled by the profound lack of mass in the voids. Think of it like a ball resting on a soft mattress. The ball will naturally roll away from the high, flat areas and down into any depressions. In the cosmos, the voids are those high, flat areas, regions of weaker gravity, while the filaments and clusters are the deep gravitational valleys. A galaxy does not just fall toward the nearest cluster, it is also constantly rolling away from the void. This dual motion is what gives the cosmic web its dynamic flow. The galaxies strung along a filament are not just hanging there motionless. They are streaming along that filament like cars on a freeway, flowing from the emptier regions toward the dense, crowded intersections where clusters form. The void is not just empty space, it is an active participant, exerting a negative pressure that herds galaxies together. This means that to predict where a galaxy like our Milky Way is going, you need a map that shows not only the glittering attractors, but also the vast, dark expanses that are pushing us toward them. Our local void, an immense region of sparse galaxies we are steadily moving away from, is as responsible for our trajectory as the Great Attractor we are slowly approaching. So the story of cosmic motion is written in both presence and absence, in the luminous pull of the crowd and the silent, expansive push of the empty deep. The universe is expanding, but not everything is moving apart. This is the crucial paradox at the heart of cosmic motion. On the grandest scales, the fabric of space itself is stretching, carrying galaxies away from each other in what astronomers call the Hubble flow. It is like dots on an inflating balloon, each dot seeing all the others recede. This smooth, relentless expansion is the background rhythm of the cosmos, the deep, steady breath of the universe. Yet if this were the only force at play, every galaxy would be an isolated island drifting forever into solitude, and the magnificent cosmic web could never have formed. The Hubble flow sets the stage, but it is not the only actor in the play. On smaller, more intimate scales, the scales of galaxy clusters, filaments, and walls, a different, more powerful force takes command. Gravity. Within these local neighborhoods, the gravitational pull of the cosmic web's immense structure is so strong that it overpowers the gentle stretching of space. Here, galaxies are not drifting apart, they are streaming together, they are falling into clusters, sliding along filaments, and being herded by voids. Their motion is a complex river current superimposed on the broader, slower tide of universal expansion. Think of it like a wide, calm ocean with a powerful local whirlpool. The ocean's overall current might be carrying water in one direction, but anything caught in the whirlpool is pulled into a frantic, circling dance of its own. The Hubble flow is the ocean current. The gravitational pull of a galaxy cluster or a dense filament is the whirlpool. Our Milky Way and every galaxy you can see is subject to both forces simultaneously. We are riding the expansion of the universe, but we are also caught in the local gravitational currents of the cosmic web, which dictate our specific path and ultimate destination. This means the simple story of an expanding universe is incomplete. To understand where any galaxy is going, you must listen to both the deep hum of space stretching and the louder, local symphony of gravity's pull. This is why a galaxy's true motion is a secret hidden in plain sight. To uncover it, astronomers must perform a kind of cosmic subtraction. They start by measuring how fast a galaxy is moving away from us, a number that combines two very different kinds of speed. The first is the predictable, smooth recession caused by the expansion of space itself, the Hubble flow. The second is the galaxy's own unique, local motion, its personal journey through the gravitational landscape of the cosmic web. This local, individual motion has a special name, its peculiar velocity. Think of it like two people on one of those moving walkways at an airport. The walkway itself is carrying everyone forward at a steady pace. That is the Hubble flow. But if one person decides to walk quickly ahead or even turn around and walk against the direction of the belt, their speed relative to the stationary airport is a combination of the belt's speed and their own effort. Their personal walking speed is their peculiar velocity. For a galaxy, its peculiar velocity is the deviation, the difference between how fast we actually see it moving and how fast it should be moving if it were only riding the smooth expansion of the universe. This deviation is not random noise, it is a direct signal, a precise measurement of the gravitational forces acting on that galaxy at this very moment. A large peculiar velocity means the galaxy is feeling a strong gravitational tug from something massive nearby, like a dense cluster or a long filament. It is being pulled off the smooth highway of cosmic expansion and onto a local gravitational on-ramp. By meticulously calculating the peculiar velocities of thousands of galaxies, astronomers can essentially reverse engineer the map of the cosmic web. They can weigh the invisible structures by watching how they make the visible galaxies sway. The peculiar motions point like arrows toward the densest concentrations of mass, revealing the hidden skeleton in exquisite detail. So when we say a galaxy is in motion, we are really telling two stories at once. One is the grand, universal story of expansion. The other is the intimate, local story of a single island of stars being guided by the invisible rivers of gravity all around it. Our Milky Way has its own peculiar velocity, a silent testament to the pull of our local filament and the push of our local void. This leads to a profound realization. Our cosmic address is not a fixed point on a static map. It is a set of coordinates that are constantly changing, carrying us toward a destiny written by the web. This journey along a filament is anything but a smooth, straight shot. It is a gravitational roller coaster, a constant tug of war where a galaxy is pulled and pushed by invisible forces from every direction. Picture a single galaxy, a brilliant swirl of stars embedded within one of those luminous threads of the cosmic web. It is not floating freely. It is caught in a complex interplay of attractions and repulsions that define its path. First, there is the immense, distant pull of the galaxy clusters that anchor the ends of the filament. These dense knots of mass act like powerful magnets, their gravity reaching out along the filament's length, drawing everything toward them. It is a slow, inexorable summons from hundreds of millions of light years away, a call to eventually join the crowded metropolis. But the galaxy is not just being pulled toward the end of the line. It is also gripped by the filament itself. This thread is not empty. It is a dense river of dark matter and hot gas, a structure with its own substantial gravitational field. So the galaxy feels a sideways pull, a force that keeps it anchored to the filament's core, preventing it from drifting off into the empty intergalactic space. It is like a raft held in the center of a strong current, guided by the banks of the river even as the current carries it forward. And then, adding another layer of complexity, is the push from the voids on either side of the filament. Those vast, empty regions exert a negative gravitational influence. Because there is so little mass there, they create a kind of slope. The galaxy, feeling stronger gravity from the dense filament and the distant clusters, effectively rolls away from the emptiness. The void does not attract, it repels, herding galaxies toward the luminous structures. So at any given moment, a galaxy riding a filament is experiencing a triple gravitational directive. It is being summoned down the line toward a massive cluster. It is being held snugly within the filament's own embrace, and it is being gently but firmly pushed from the sides by the expanding nothingness of the voids. Its actual motion is the sum of these vectors, a spiraling, sliding, uncertain path that is anything but a straight line. This dynamic explains why galaxies within a filament often appear to move in streams and groups, like cars jostling in lanes on a highway, some accelerating, some merging, all responding to the same invisible landscape. Their dance is a direct readout of the gravitational forces sculpting the local universe, a silent testimony to the push and pull of an unseen architecture. Mapping this gravitational dance for a single galaxy is one thing, but to truly understand the cosmic web's grand choreography, we need to run the universe in reverse. We need to witness its entire growth from a smooth, hot beginning to the intricate network we see today. This is not possible with telescopes alone, as they can only show us snapshots of different cosmic eras. To see the movie, we turn to one of the most powerful tools in modern cosmology, the supercomputer simulation. Projects with names like Millennium and IllustrisTNG are not video games. They are virtual universes born from equations and raw computing power, designed to test our deepest theories about how everything came to be. The process begins with a simple, almost featureless starting point, a digital representation of the infant cosmos just after the Big Bang. This virtual universe is filled with a nearly uniform sea of particles, both dark matter and ordinary gas, seeded with the exact same tiny density ripples we detect in the cosmic microwave background, the afterglow of creation itself. Then, with the press of a button, the simulation begins. The only rule is gravity. Billions of virtual particles, each representing a vast cloud of dark matter, start to feel each other's pull. Over millions of simulated years, gravity works its relentless magic. The slightly denser regions attract more matter, growing denser still. The underdense regions are drained, becoming emptier. What starts as a nearly smooth soup begins to curdle, then to clump, and then to stretch. Astonishingly, without any further instructions, the simulation weaves its own tapestry. Filaments emerge, connecting at dense nodes. Vast voids open up and expand. Galaxies form along the luminous threads, drawn into clusters at the intersections. The virtual universe, governed solely by the known laws of physics, spontaneously generates a cosmic web that looks almost identical to the one we painstakingly map with our telescopes. This is a profound validation. It tells us that the simple ingredients of dark matter, ordinary matter, and gravity are not just enough to explain the web, they demand it. The fact that our simulated universes grow up to look like our real one means we are on the right track. We are not just observers of this architecture, we are beginning to understand the blueprints. Those simulations reveal a startling truth. The blueprint for the entire cosmic web was drawn in the first fraction of a second of existence. The origin of this universal architecture lies in the most delicate of beginnings, not in a cataclysm, but in a whisper. In the unimaginably hot, dense fireball of the newborn universe, a brief and explosive event called cosmic inflation stretched space itself faster than the speed of light. This process did more than just rapidly expand everything. It also magnified the tiniest possible ripples in reality, quantum fluctuations that were popping in and out of existence on a scale trillions of times smaller than an atom. Inflation took these fleeting, ghostly murmurs of more and less and stretched them across the entire cosmos, freezing them into the very fabric of space as minute differences in density. Think of a perfectly smooth, still pond. At the quantum level, it is never perfectly still. There are always tiny, random ripples on its surface, far too small to see. Now imagine the pond suddenly and violently expanding to the size of an ocean in an instant. Those tiny ripples would be stretched into vast, gentle swells and troughs that now cover the entire expanse. That is what inflation did to the infant universe. It imprinted a faint pattern of hills and valleys in the distribution of matter and energy, a pattern of overdensities and underdensities that was absolutely microscopic, but now existed on a cosmic scale. These were the seeds. For hundreds of thousands of years, nothing much happened on a structural level. The universe was still too hot and energetic for atoms to even form, a swirling plasma of particles and light. But gravity is patient. Once the universe cooled enough for atoms to coalesce and for light to finally travel freely, gravity went to work on that imprinted pattern. The slightly denser regions, the hills in that cosmic landscape, had a tiny bit more gravitational pull than their surroundings. They began to attract nearby matter, growing ever so slightly denser. The underdense regions, the valleys, lost matter to their denser neighbors, becoming emptier. It was an amplifying feedback loop that ran for billions of years. A whisper of more became a murmur, the murmur became a shout, and the shout eventually sculpted the grand canyons and mountain ranges of the cosmic web. The great filaments we see today are the descendants of those initial, stretched quantum ripples. The immense voids are the grown-up children of the initial underdensities. So when you look at a map of the cosmic web with its filaments spanning hundreds of millions of light years, you are not just looking at structure, you are looking at the magnified fingerprint of the universe's first moment, a quantum signature written across the sky. This means the destiny of every galaxy, including our own, was subtly hinted at in those first chaotic instants, a fate written in a language of probability and gravity long before the first star ever ignited. The type of dark matter matters immensely for the kind of universe we get. In the early days of cosmic web theory, scientists explored different possibilities. They considered a model called hot dark matter, where the particles would have been moving at nearly the speed of light in the early universe. This scenario creates a universe that is smooth and elegant, but it has a critical flaw. Those fast-moving particles would have streamed right through the tiny density ripples left by inflation, smoothing them out before they could grow. gravity would have had nothing substantial to grab onto, preventing the early, small clumps needed to eventually build galaxies and filaments. The universe would have remained too uniform, a cosmic soup that never curdled into interesting structure. The web we see simply could not form. The model that succeeded, the one that matches our observed reality, relies on cold, dark matter. Cold here does not refer to temperature in the everyday sense, but to speed. Cold, dark matter particles in the early universe moved sluggishly compared to the expansion of space. They were slow, heavy, and ponderous. This slowness was the key to everything. Because they were moving so slowly, these particles could not escape their own tiny gravitational pull. When they found themselves in one of those microscopic overdensities, a whisper of more, they stayed there. They clumped together efficiently from the very start, amplifying those initial seeds into the first gravitational wells. Think of it like trying to build a sandcastle on a windy beach with two different types of sand. Hot dark matter is like fine, dry dust. The wind, representing the expansion of the early universe, blows it away before you can shape it into anything. Cold dark matter is like wet, heavy sand. It sticks together, you can mold it, and it holds its shape against the breeze. That sticking, that efficient clumping on the smallest scales, is what allowed the universe to build its grand architecture from the bottom up. Tiny clumps merged into larger clumps, which then drew in gas and began to light up as the first proto-galaxies. These building blocks then became attracted to each other along the lines of the growing dark matter skeleton, tracing out the filaments and gathering at the nodes. Without cold dark matter's patient gravitational stickiness, the cosmic web would be a faint, blurry sketch. With it, the universe became a detailed and intricate sculpture. So the magnificent filamentary structure we observe is not just evidence for dark matter, it is very specific evidence for the cold, slow-moving kind, the cosmic clay that could hold the imprint of creation's first whisper. The dark matter skeleton was complete, a silent and invisible framework spanning the cosmos, but a scaffold alone does not make a city. It needs buildings, lights, life. This is where ordinary matter, the stuff of stars and planets and us, finally enters the story. For hundreds of millions of years after the Big Bang, the universe was a featureless, hot fog of hydrogen and helium gas, searingly bright and impenetrable. This gas, which scientists call baryonic matter, was utterly dominated by the gravitational might of the dark matter. It had no choice but to follow the leader. As the dark matter web condensed into its vast network of filaments and nodes, it carved deep gravitational valleys into the fabric of space. The ordinary baryonic gas, now finally cooling as the universe expanded, began to flow. It streamed like water down a mountainside, following the paths of least resistance into the waiting arms of the dark matter structure. This was not a gentle trickle. It was a colossal, cosmic river system, with currents of gas surging along the filaments at millions of miles per hour, funneling toward the dense intersections where galaxy clusters would eventually blaze to life. The gas did not just flow, it transformed. As it raced into these gravitational wells, it compressed, and as it compressed, it heated up, glowing fiercely with X-ray light. But then something critical happened. Within these dense, hot streams, pockets of gas began to cool. They radiated away their immense thermal energy, allowing them to condense further. Think of steam rising from a boiling kettle hitting a cold window. The gas condenses into droplets. On a cosmic scale, these cooling droplets within the filaments were the seeds of galaxies. A knot of gas would cool, collapse under its own gravity, and begin to spin. And within that spinning, collapsing cloud, the first stars ignited. Their brilliant light pierced the primordial fog, and a galaxy was born. This process did not happen randomly in empty space. It happened precisely along the luminous threads of the cosmic web, because that is where the dark matter had concentrated the raw material. The galaxies lit up like street lamps along a pre-built highway. tracing the invisible infrastructure beneath them. So when we look out and see a beautiful string of galaxies, a filament in the cosmic web, we are seeing the aftermath of this ancient, obedient flow. We are seeing where the ordinary matter finally settled, lighting the blueprint that was drawn for it billions of years before. The stars are not the structure, they are the decoration, the glorious, shining proof that the dark matter's plan worked perfectly. This leaves us with a crucial distinction to grasp, one that changes how we see every image of the cosmos. The brilliant galaxies we observe are not the cosmic web itself. They are merely the tracers, the bright markers that allow us to see its hidden contours. Picture a sprawling highway network seen from an airplane window at night. You do not see the dark asphalt of the roads. Instead, you see the glowing streetlights and the headlights of cars, strung in long, graceful lines and clustered at massive interchanges. Those lights reveal the precise layout of the transportation network, tracing every curve, every on-ramp, and every major hub. But the lights are not the highway. They are simply riding upon it, illuminating its path. In our universe, galaxies are those streetlights. The cosmic web is the dark, foundational highway system of dark matter and diffuse gas. We map the web by observing where the galaxies, those points of light, have chosen to gather. Their luminous patterns sketch out the invisible architecture beneath. A dense knot of galaxies reveals a massive gravitational anchor point. A long, thin chain of galaxies traces the path of a dark matter filament. A vast, empty region with only a few lonely pinpricks of light outlines the border of a void. Every survey, every three-dimensional map we create, is essentially a long exposure photograph of the universe's streetlights, from which we must infer the shape of the roads. This means when we marvel at an image of the cosmic web, we are engaging in a profound act of interpretation. We are seeing the effect, not the cause. The true structure is the gravitational landscape, the rivers of unseen matter. The galaxies are simply the most visible inhabitants that settled in the most desirable neighborhoods, their collective glow providing the only map we have to this hidden world. So the next time you see a visualization of those delicate filaments stretching across the void, remember you are looking at a census of lights, a guidepost to something far greater and more mysterious than light alone can show. Our place in this universal tapestry is not some distant, abstract coordinate. We have a local address, a specific neighborhood within the cosmic web that dictates our every move. We live within a structure known as the local sheet, a vast, flat wall of galaxies that includes our Milky Way, the Great Spiral of Andromeda, and dozens of smaller galactic companions. Think of it as our galactic continent, a sprawling, thin plain where most of the galaxies we see with the naked eye reside. This sheet is not floating in isolation. It is one wall in a much larger local complex, and it defines the plane of our immediate gravitational reality. On one side of this sheet, pressing against it, is an immense and profound emptiness called the local void. This is a region of space hundreds of millions of light years across that contains almost no galaxies, a true cosmic desert. Its gravitational influence is not a pull but a push. The lack of mass there means we are effectively rolling away from it, down a gentle slope into the denser parts of the web. This void is one of the great forces herding our local group of galaxies along its path. And that path has a clear direction. Our entire local sheet, with the Milky Way riding along within it, is flowing. We are caught in a vast, silent river of galaxies, all moving together toward a mysterious gravitational anomaly known as the Great Attractor. This is not a single object, but a massive concentration of mass hidden behind the dense plane of our own galaxy's central bulge, making it difficult to observe directly. It is the gravitational heart of our local supercluster, a focal point pulling thousands of galaxies, including our own, toward its center. But the story does not end there. Recent, more precise mappings reveal that our motion is part of an even grander pilgrimage. The Great Attractor itself, and all the galaxies flowing into it, are being pulled toward something far more immense, the Shapley supercluster. This is one of the largest known structures in the observable universe, a staggering concentration of mass containing tens of thousands of galaxies, a true gravitational titan lying over 600 million light-years away. So our journey is a nested one. We are sliding along our local sheet, pushed by the local void, drawn toward the Great Attractor, which is itself falling toward the Shapley supercluster. Every bit of this motion, from the gentle drift of our nearest galactic neighbors to the immense flow of entire superclusters, is a direct consequence of our position within the cosmic web's gravitational landscape. Our destiny is written in the push of voids and the pull of clusters, a voyage set in motion when the universe was just a whisper. For decades, the Great Attractor existed only as a ghost in our data. Astronomers in the 1970s and 80s, while charting the motions of galaxies, noticed something deeply unsettling. Every galaxy in our local region, including the Milky Way, was not just drifting with the universe's expansion. It was being pulled with immense force toward a specific point in the sky, a point hidden behind the thick, dusty heart of our own galaxy in the constellation Centaurus. This mysterious, unseen concentration of mass was dubbed the Great Attractor, and it felt like a cosmic phantom, a gravitational siren calling us toward something we could not see. The Milky Way was rushing toward this point at over 600 kilometers per second, a staggering speed that hinted at a mass equivalent to tens of thousands of galaxies. Yet when telescopes looked in that direction, they saw mostly the obscuring veil of our own galactic plane. It was a profound scientific mystery, a dark, massive something that seemed to defy observation. The enigma was not just about what it was, but what it meant for our understanding of the universe. If such a colossal mass could hide in plain sight, what else were we missing? Was our map of the cosmos fundamentally flawed? The Great Attractor became a symbol of our cosmic ignorance, a reminder that for all our powerful telescopes, the universe still held colossal secrets just out of view. It fueled speculation and wonder, a tangible proof that we were not just passive observers, but participants in a vast, unseen flow. We were being hauled toward an unknown destination by an invisible hand, and for a time we had no idea what that hand belonged to. The key to solving this mystery lay not in looking harder at the one spot, but in finally seeing the bigger picture provided by the cosmic web. As large-scale redshift surveys began to pierce through the galactic dust and map the universe in 3 dimensions, the ghost began to take shape. The Great Attractor was not a single, monolithic object like a supermassive black hole. It was something far more fitting to the architecture of the cosmos. It was a gravitational confluence, a major intersection in the cosmic web where several immense filaments of dark matter and galaxies came together. At this junction sat not one, but several massive galaxy clusters, including the Norma cluster, all bound together in a vast supercluster of staggering mass. This demystified the phenomenon completely. The pull we felt was not from a singular, mysterious entity. It was the combined gravitational pull of an entire metropolitan hub of the universe, a grand central station of the cosmic web hidden behind a curtain of dust. Our motion was not an anomaly, it was the most natural thing in the world. We are part of a local wall of galaxies, and our entire wall is flowing down a gravitational slope toward the nearest major node in the web, just as water flows toward a drain. The Great Attractor was simply the name we gave to that drain, that focal point. Mapping the web transformed it from a frightening phantom into a predictable landmark, a testament to the power of seeing the universe not as isolated points of light, but as a connected, flowing structure. Our journey toward it is not a mystery, but a confirmation of the web's governing power. this gravitational journey we are on leaves a permanent signature in the oldest light we can see. The cosmic microwave background, that faint afterglow from the birth of the universe, is often described as a perfect, uniform glow, the ultimate baby picture of the cosmos. But when scientists first mapped it with exquisite precision, they found it was not perfectly smooth. It carried a subtle yet unmistakable pattern that had nothing to do with the infant universe and everything to do with our motion through the cosmic web today. The map revealed a dipole anisotropy. In simpler terms, one half of the sky appears very slightly warmer or hotter in this ancient light, while the opposite half appears very slightly cooler. This is not a feature of the early universe. It is a wake, a Doppler effect created by our own movement. Think of walking through a gentle, misty rain. If you stand still, the rain falls evenly on your face and shoulders. But if you start walking forward, you will feel more droplets hitting your front and fewer hitting your back. From your moving perspective, the rain appears to be coming from ahead of you. The cosmic microwave background is like that universal mist, a bath of photons raining down on us from all directions. Because our entire galaxy is rushing through the cosmic web toward the Great Attractor at over 600 kilometers per second, we are plowing into this radiation head-on. The photons coming from the direction we are moving toward get squeezed, their wavelength shortened, making that region of the sky appear slightly hotter. The photons coming from behind us, the direction we are fleeing, get stretched out, making that part of the sky appear slightly cooler. This hot and cold spot is our personal fingerprint on the oldest light in existence. It is a direct, measurable consequence of our peculiar velocity, that local motion superimposed on the universe's expansion. By measuring the exact temperature difference between these two poles, astronomers can calculate our speed and direction with incredible accuracy. That calculation points us precisely along the flow we have been describing, pushed from the local void and pulled toward the gravitational confluence of the Great Attractor. So the cosmic web is not just something we map with distant galaxies. Its influence is etched into the most fundamental canvas of the cosmos. Our motion through its invisible architecture has literally painted a hot and cold spot across the sky, a permanent testament written in the first light of creation. This flow is not a gentle drift but a powerful, directed current. Within the grand architecture of the cosmic web, the filaments act as immense rivers of gravity, and the galaxies within them are like leaves caught in the stream, their fates shaped by the strength and direction of the flow. These are not peaceful rivers, they are cosmic conduits of unimaginable scale, funneling vast quantities of raw material hydrogen gas and dark matter from the sparse hinterlands of the universe directly into the bustling metropolitan centers, the galaxy clusters. The entire system operates like a watershed. Smaller, thinner filaments act as tributaries, merging and feeding into larger primary rivers. These great rivers then converge at the nodes, the clusters, delivering a continuous supply of fuel for star formation and feeding the supermassive black holes that lurk at the hearts of galaxies. This gravitational watershed dictates everything about a galaxy's journey. It determines the path it will take over billions of years, steering it toward inevitable mergers with other galaxies traveling along the same stream. It can even influence the galaxy's very spin, aligning the axes of rotation for galaxies within the same filament, as if they are all rolling down the same slope. When we look at a galaxy cluster, we are not just seeing a static crowd. We are witnessing the terminus of countless rivers, a place where cosmic streams have delivered their passengers to a final, crowded destination. Our own Milky Way is riding one of these streams within our local sheet, a tributary flowing toward a larger confluence, caught in a current that was set in motion long before our sun was born. Galaxy clusters are the final destinations on the cosmic web's great highways. These are not peaceful places. They are the universe's most crowded and violent metropolises, and their entire existence is governed by the flow of the filaments that feed them. A cluster like Coma or Virgo is a gravitational monster containing the mass of 1,000 Milky Ways, with hundreds of individual galaxies swarming in a frenzied orbit around a common center. But none of this would exist without the relentless delivery service of the Web. The cluster sits at the intersection of several major filaments, a grand central station where the cosmic rivers converge. Along these rivers, galaxies and vast clouds of hot gas stream inward, accelerating as they approach the cluster's immense gravitational well. This process is called accretion, and it is how a cluster grows from a modest gathering into a titan. The filaments act as organized channels, directing this incoming traffic in specific, predictable patterns. Galaxies do not fall into a cluster from random directions. They arrive in streams like commuters pouring off a train platform, all coming from the same direction dictated by the filament they rode in on. This means a cluster's growth history is literally written in the orbital paths of its member galaxies. By studying how galaxies move within a cluster today, astronomers can trace them backward, reconstructing which filament they arrived from, and even when they joined the swarm. It is cosmic archaeology, using motion to read a history of construction. These arrivals are not gentle mergers. A galaxy falling into a cluster for the first time experiences a brutal environment. It is ripped through a sea of superheated gas that can strip away its own star-forming fuel in a process called ram pressure stripping. Its delicate spiral arms can be stretched and distorted by the tidal forces of so many close neighbors. Often it will collide and merge with another incoming galaxy, their stars mingling to form a new, larger, and often featureless elliptical galaxy. The cluster, in essence, homogenizes its residents, erasing their individual histories to create a population of old, red, and rounded galaxies. All of this chaos, the stripping, the collisions, the transformations, is orchestrated by the Web. The filament determines the timing, the angle, and the speed of a galaxy's arrival. It sets the stage for every merger and every disruption. So when we look at a serene image of a distant galaxy cluster, we are not looking at a static snapshot. We are looking at the bustling terminus of a billion-year delivery system, a place where the cosmic web's rivers finally empty their contents into a deep gravitational sea. This immense emptiness is not just a backdrop, it is one of the most powerful engines shaping the universe. We have thought of voids as the silent deserts between the glittering cities of the cosmic web, but that view is incomplete. These vast regions of near-nothingness are not passive. They are actively expanding, and in doing so, they are sculpting the universe as much as gravity itself. To understand this, we must shift our perspective. The cosmic web is not a static sculpture. It is a dynamic, evolving system, and the voids are its growing chambers. As the universe expands, the voids, which are already underdense, become even emptier. They stretch, their boundaries pushing outward into the surrounding regions. Think of a balloon inflating inside a box of marbles. As the balloon grows, it pushes the marbles aside, herding them into the corners and along the edges of the box. The marbles are not attracted to the balloon, they are repelled by its expansion. In our cosmos, the galaxies are the marbles and the voids are the growing balloons. The boundary of a void is not a sharp edge but a slope, a gravitational gradient. On one side, you have the profound lack of mass in the void. On the other, you have the dense concentration of mass in a filament or a wall. A galaxy near this boundary feels a powerful imbalance. It is not so much pulled toward the filament as it is pushed away from the void. The expanding emptiness creates a pressure that shepherds galaxies, guiding them into the luminous structures that outline its borders. This is why filaments and walls often appear so sharp and well-defined. They are not just where matter gathered, they are where matter was corralled. The voids act as cosmic ranchers, using their expansion to herd the galactic cattle into the pens of the web. So a galaxy's journey is not a simple fall toward a cluster. It is a more complex escape, a flight from the growing nothingness into the crowded embrace of something. This motion from void to filament is a fundamental current in the cosmos, a silent exodus driven by absence. The cosmic web's influence reaches even into the very spin of a galaxy. This is one of its most subtle and profound signatures, a fingerprint left on the internal rotation of every star city by the gravitational tides that shaped its birth. For a long time, astronomers assumed that a galaxy's spin was random, a product of the chaotic, swirling collapse of its initial gas cloud. The direction it chose to rotate, clockwise or counter-clockwise from our perspective, seemed like a cosmic coin toss. But as our maps of the web grew more precise, a startling pattern emerged. Galaxies do not spin at random. Their axes of rotation, the imaginary lines running through their poles, show a distinct preference. They tend to align with the cosmic filaments they inhabit. A galaxy living within a long, thin thread of the web is more likely to spin like a bullet fired along the length of that thread, its axis pointing parallel to the filament's direction. Others may spin like a wheel rolling along the filament, their axis perpendicular. But the key is this: the spin is not random. It is correlated with the larger architecture. This alignment is a direct fossil, a memory of the galaxy's formation process within the flowing currents of the web. When a proto-galaxy first condenses from gas flowing along a dark matter filament, it is not forming in empty, still space. It is condensing within a powerful river of gravity. The tidal forces from the massive filament itself, the stretching pull along its length, and the squeezing pressure from the voids on either side, impart a subtle torque on the collapsing cloud of gas. This torque acts like a gentle hand on a spinning top, guiding its initial rotation to align with the flow of the river that bore it. The galaxy retains this alignment for billions of years, a quiet testament to its ancient journey. So when we measure the spin of a distant spiral galaxy, we are not just learning about its internal dynamics. We are reading a compass that points back to the filamentary highway it was born on. This discovery transforms galaxies from isolated islands into embedded structures, their very rotation a permanent record of the cosmic currents that birthed them. This elegant picture of the cosmic web holds a glaring omission, a missing piece of the universe's inventory so large it challenges our basic accounting. For all our maps and simulations, we have only ever found about half of the ordinary matter the Big Bang should have produced. This is known as the missing baryon problem, and it is one of cosmology's most persistent puzzles. Baryons are the particles that make up everything you can see, touch, or be, the protons and neutrons in stars, planets, and us. According to our best models of the early universe, a specific amount of this stuff was created. Yet when we tally up all the stars in all the galaxies, all the cold gas clouds, and all the hot plasma in galaxy clusters, the numbers fall dramatically short. Where did nearly half the atoms in the cosmos go? The most compelling answer lies in the most difficult places to look, the vast, empty-looking spaces between the galaxies. Scientists now suspect the missing baryons are not missing at all. They are hiding in plain sight, spread so thin and heated so intensely that they are virtually invisible to our traditional telescopes. This matter likely exists as a searing, diffuse fog of gas known as the warm-hot intergalactic medium, and it is concentrated precisely along the filaments of the cosmic web. Think of trying to see a single, faintly glowing thread stretched across a dark room from miles away. Our telescopes, designed to capture the brilliant pinpoints of stars and galaxies, have struggled to detect this tenuous, web-like haze. It is like mapping a city at night using only the brightest streetlights, while the entire network of dimly lit roads remains unseen. This hot, filamentary gas is the final reservoir, the universe's hidden stockpile of ordinary matter. It is the glue that connects the luminous galaxies, the medium through which the web's gravitational currents truly flow. Finding it would not just solve an accounting error, it would complete our picture of the cosmic architecture, proving that the web is not just a dark matter skeleton, but a structure richly woven with the very atoms of creation. Detecting this faint cosmic fog is one of the greatest observational challenges in modern astronomy. The warm, hot intergalactic medium is not a dense cloud you can simply photograph. It is an incredibly tenuous gas, so diffuse that a single cubic meter of it might contain only a single atom. Yet it stretches for millions of light years, and that immense volume adds up to the missing half of all ordinary matter. To find it, astronomers cannot look for light it emits because it glows far too feebly. Instead, they must become cosmic detectives, looking for the shadow it casts against a brilliant background light. Their most powerful tool is the quasar, a beacon from the early universe. Quasars are the intensely luminous cores of distant galaxies, powered by supermassive black holes feasting on matter. They shine with the light of 1 trillion suns, acting as cosmic lighthouses whose beams travel across billions of light years to reach us. As that brilliant light passes through the universe, it journeys through the filaments of the cosmic web. When it encounters the warm, hot intergalactic medium within those filaments, specific wavelengths of light are absorbed by the superheated atoms in the gas. This leaves dark, narrow gaps in the quasar's otherwise smooth spectrum of colors, like unique barcodes imprinted on the light. By analyzing the precise pattern of these absorption lines, scientists can determine the composition, temperature, and density of the invisible gas the light passed through. It is a form of cosmic tomography, using a distant quasar's beam to illuminate the anatomy of a filament we could never see directly. Each absorption line is a whisper from the hidden web, a direct confirmation that the space between galaxies is not empty but richly structured. Another crucial technique looks not for shadows but for a faint, diffuse glow. The gas in the densest parts of filaments is heated to temperatures of millions of degrees, causing it to emit very low-energy X-rays. Satellites like the Chandra X-ray Observatory and XMM Newton are designed to be sensitive to this specific, soft emission. They do not see sharp images of filaments, but rather a faint, blurry haze that traces the space between galaxy clusters, exactly where the models predict the web's rivers should be. Combining these two methods, the absorption shadows in quasar light and the faint X-ray glow, is giving us our first crude maps of the cosmic web's gaseous content. We are moving from inferring the web's structure through the galaxies that light it up to beginning to sense the dark rivers themselves. This is the frontier of cosmic cartography, where we are no longer just mapping the streetlights, but starting to see the faintly glowing outline of the roads. The universe's grand architecture is not frozen in time. It is a living, breathing structure, constantly reshaping itself according to the relentless dictates of gravity. If we could watch the entire history of the cosmos play out on fast forward, the cosmic web would not simply appear and hold its form. It would writhe and transform, its delicate threads thickening, its great knots swelling, in a slow-motion dance of construction and destruction that spans billions of years. This evolution is written into the very fabric of the web, a story of growth from a whisper to a roar. In the universe's youth, just a few billion years after the Big Bang, the cosmic web was a masterpiece of fine detail. Simulations show it as an intricate, delicate lacework, with countless thin, gossamer filaments spreading out like the capillaries of a leaf. These threads connected a vast number of small, young galaxy clusters, creating a densely interconnected network where matter flowed along many narrow pathways. It was a universe of bustling small towns, all linked by a sprawling system of backroads, but gravity is a patient sculptor with a preference for consolidation. Over time, the smaller does not survive. The relentless pull of larger structures begins to dominate. Smaller filaments, tugged by the stronger gravity of their more massive neighbors, begin to merge and funnel their material into larger primary channels. It is akin to watching a river system mature. Small streams converge into creeks, creeks flow into rivers, and rivers merge into mighty, singular waterways. In the cosmos, this means the fine web coarsens. Those countless delicate threads gradually vanish, their material and the galaxies they carried absorbed into a smaller number of much thicker, more massive filaments. These become the superhighways of the later universe, carrying titanic rivers of gas and galaxies toward ever-growing destinations. Simultaneously, the clusters at the intersections grow from modest towns into colossal metropolises. As the thickening filaments deliver more and more material, these gravitational hubs feast. Galaxy clusters merge with one another in violent, slow-motion collisions, absorbing entire groups of galaxies and amassing staggering amounts of dark matter and hot gas. The voids, too, participate in this evolution. As the web coarsens, the empty regions between the filaments don't just sit there, they expand and merge as well. Smaller voids combine to form even vaster, emptier supervoids, their growing emptiness further defining and sharpening the borders of the remaining luminous structures. So the universe we see today, with its stark contrast between a few massive filaments, enormous voids, and brilliant, dense clusters, is merely the current frame in a very long movie. It is a middle-aged cosmos where the initial fine lace has been woven into a heavier, more simplified tapestry. The web of tomorrow will be coarser still, with gravity continuing to draw everything into an ever smaller number of unimaginably large conglomerations. This means the Milky Way's current journey is just one chapter in an epic that began with the first quantum whisper and will end in a distant future of darkened, merged giants. Yet for all its predictive power, this elegant model of dark matter and cosmic expansion is not without its open questions. The cosmic web itself, in its precise details, is presenting astronomers with subtle but persistent puzzles that challenge the edges of our understanding. The standard cosmological model, known as Lambda-CDM, has been phenomenally successful. It describes a universe dominated by dark energy and cold dark matter, and it predicted the large-scale filamentary structure we now observe. However, as our maps of the web grow more detailed and more precise, certain features are emerging that do not align perfectly with the model's simulations. These are not catastrophic failures, but intriguing tensions, whispers that the full story may have nuances we have yet to grasp. For instance, some of the voids we observe appear to be larger and emptier than the simulations tend to produce. In a universe governed by the standard model, matter should be distributed in a specific statistical way, leading to voids of a predictable range of sizes. But when we look out, we find cavernous, empty regions that stretch the boundaries of those predictions. Their sheer scale and profound emptiness raise a fascinating question. Did gravity have more time, or perhaps a different set of initial conditions, to sculpt these deserts than our best models allow? Similarly, the statistics of the filaments themselves, their thickness, their connectivity, and the way galaxies are distributed along them, sometimes show slight but measurable deviations from what supercomputer universes generate. Some studies suggest the web might be slightly more pronounced or structured differently on the largest scales than Lambda-CDM anticipates. These discrepancies are not evidence that the entire framework is wrong. Far from it, they are more like finding a single, puzzling thread in an otherwise perfectly woven tapestry. They indicate that our model, while overwhelmingly accurate, might require subtle refinements. Perhaps the nature of dark matter is slightly more complex than the simple, cold, slow-moving particle we have assumed. Maybe dark energy, the force driving the universe's accelerated expansion, has not been constant over time as we think. Or it could be that the initial seeds from inflation had a more intricate pattern than we have accounted for. These challenges are not weaknesses in science, they are its lifeblood. Each tiny tension between observation and prediction is a new frontier, a clue that pushes us to look deeper, simulate more accurately, and think more creatively. The cosmic web is not just a structure to map, it is the ultimate testing ground for our theories of everything. These subtle tensions in the cosmic map are not dead ends, they are signposts pointing toward a new era of discovery. The next generation of cosmic cartography is already underway, with instruments of staggering power designed to map the web with a precision we have only dreamed of. The Vera C. Rubin Observatory, currently under construction in Chile, will perform a 10-year survey of the entire southern sky, imaging billions of galaxies and detecting subtle distortions in their shapes caused by the gravitational lensing of dark matter filaments. It will essentially take a high-definition movie of the cosmic web's growth over time. Simultaneously, the European Space Agency's Euclid satellite is now in space, creating its own immense three-dimensional map to measure the geometry of the dark universe. And looking further ahead, the Square Kilometre Array, a radio telescope network spanning 2 continents, will peer back to the universe's infancy, tracing the distribution of neutral hydrogen gas that painted the earliest strands of the web. Together, these projects will provide a definitive census. They will not just map where galaxies are, but will precisely chart how they move, how the web's structure has evolved over billions of years, and how dark energy has been stretching the cosmic fabric. This flood of data will act as a supreme test. Every proposed tweak to our models of dark matter, dark energy, or even gravity itself will have to pass the ultimate exam, reproducing the exact, intricate details of the web we finally see. The universe's largest structure is about to become its most stringent laboratory. The entire universe operates on a chain of command, a hierarchy of control that flows from the smallest possible scale to the grandest. It begins with a whisper, a quantum murmur in the first fraction of a second of existence. Those random, microscopic ripples were stretched across the cosmos by inflation, becoming the faint but universal blueprint of overdensities and underdensities. This blueprint was not written for the stars but for the dark matter. The dark matter, cold and slow, obediently clumped around those imprinted seeds, its overwhelming gravity constructing the first scaffolds of the cosmic web. This invisible skeleton then became the master architect for everything that followed. Its gravitational valleys and mountains dictated the flow of all ordinary matter, channeling rivers of hot gas along its filaments and into its dense nodes. This flow, in turn, created the galaxies, lighting up the blueprint like neon signs along a pre-built highway. But the control does not stop at placement. The web's gravity generates the peculiar velocities, those deviations from the Hubble flow that reveal a galaxy's personal journey through the landscape. It is this velocity that steers a galaxy's long-term trajectory, determining whether it will slide peacefully along a filament or be hurled into the violent core of a cluster. It influences a galaxy's spin, aligns it with its cosmic river, and even dictates its fate through mergers and transformations. From quantum seed to dark matter scaffold, from gravitational river to galactic destiny, this is the unbroken chain. Every galaxy, including our Milky Way, is a passenger on this ride, its past, present, and future authored by the invisible currents of an architecture born from the first whisper of time. This means the story of a galaxy is never just its own. Its past is written in the filament that birthed it, its present defined by the gravitational current it rides, and its future determined by the destination toward which that current flows. To truly know a galaxy, you cannot simply look at its stars. You must look at its address within the cosmic web and the silent river carrying it forward. This grand architecture of gravity is the universe's ultimate organizing principle. the hidden framework that turns random starlight into a coherent, flowing narrative. We have moved from seeing islands in a void to understanding passengers on a current, from mapping isolated points to tracing the contours of an invisible landscape. Every discovery, from the peculiar velocity of the Milky Way to the hot and cold spots in the ancient sky, confirms our embeddedness within this dynamic system. So the next time you look up at the night sky, remember you are not just looking out into space. You are looking from within a moving vehicle, a star city sailing on a river of dark matter, pushed by voids and pulled by clusters, on a journey set in motion when the cosmos was just a whisper. Your place is not a static point on a map, but a set of coordinates in a story billions of years in the telling, written in the language of gravity and the architecture of light.